So first of all, I'd like to thank Hutchinsons for the invitation to come to this marvellous conference. I'm going to be focusing in on soils. I know Keris gave me a lot of things to answer, but in 20 minutes, I'm going to focus on soils. We can talk about other things in the panel discussion, I'm sure. Okay, so what I'm going to be talking about is building soil carbon and trying to get to what are realistic goals in terms of storing carbon in soil. What have we learned and how do we actually go about this? And I hope that during this morning, this conference, there'll be more and more practical detail about how to do this. But I want to set out some of the ground rules in terms of what we've learned, what's important, what we need to know. So what do I need to know about storing carbon in soil? Well, I've boiled it down to at least 6 things that you need to know. And I can illustrate them, I think, quite nicely with one of our most famous experiments. This is the Rothamsted experiment called Broadbork. It's actually the longest scientific experiment in the world, actually, started in 1843. And it can illustrate these important points that we all need to know very nicely, I think. So the first of all is, if you are storing carbon in soil, it reaches a new equilibrium. It doesn't go on forever. And you can see that quite clearly here. At Rothamsted, we started adding here either farmyard manure, the red one, that shoots up, or we changed to woodland from arable. It shoots up. You can see that. But the point is, it won't go on forever. And you can see from the blue line here, and even this one here, which is the arable treatment, it's coming to another equilibrium. It's coming to a plateau, in other words, and you're not going to store more and more. The most rapid change happens near the beginning in both arable and woodland systems, when you change the management, and then it goes towards this new equilibrium. And then the second point that we can illustrate very nicely from our experiments is, if you then convert again, change your management, it will decline fairly quickly. So it's not permanent, it's reversible. And Keris mentioned this. Administrators and governments want to know that if you're storing carbon in soils, that it will stay there for quite a long time. And that's a very important point. You know, if you get paid for storing carbon in the soil and you change management in some way that does this, they're going to want their money back. You know, you have to really try to say, okay, we're going to keep it in the soil for, let's say, 50 years, 100 years, if it's going to make a difference. And then the third point is additionality. Already, many farmers are managing the land and returning, for example, residues and cover crops and all this sort of thing. If we're going to store more carbon in soil, it's got to be additional to what you're doing already, business as usual. So what are the things that are going to be additional and are going to boost carbon above what's already being done? The permanence I've already covered, so the length of time. The leakage. Leakage is what Keris mentioned about. The most famous example is don't do anything which means that there's going to be more production and clearance, for example, of rainforests. That's not going to help the overall carbon in the world, basically. And then finally, I think one of the most important things is the availability of organic matter to add to the soil if you want to boost carbon storage. Because, you know, there's only so much organic matter. Where do you get it from? And actually, this whole thing of storage, if you think about it, is driven by, well, it's originally driven by photosynthesis, productivity, and organic carbon. And if you're already doing things, this comes back to the additionality. If you're already doing things, where do you find that extra carbon? Okay, so going a little bit deeper into the carbon storage, what do we know in terms of the science? So the binding of organic carbon is often with mineral particles in soil, and this protects the soil organic carbon. So in this picture here, the organic carbon is the brown bits, and the sort of light yellow stuff is clay and mineral particles. And these are really, really small. That says 10 micrometers there, 10 thousandths of a millimeter, 10 millionths of a millimeter. Really small stuff. And actually, these are other soil particles, and there are soil organisms, and there's even, voids and water in soil. Big organic matter, let's say, might be existing out here, but it then decays very quickly. What we're really interested in is how to get carbon in there, as I said, and have it stored for some length of time. And actually what we find is the amounts of clay, particularly, they're very related to soil structure, but also protects that organic matter, even from organisms and even from the enzymes that organisms put out to degrade organic matter. And so we want to increase this stuff, which is protected. And the other important fact is that we know you have to add about 10 times more organic carbon annually than you expect to stay in the soil. So in other words, 90% is actually broken down and released back to the atmosphere, particularly the big stuff, as I said, the stuff that exists at this sort of level outside of the protection by organominerals in the soil. So given that background, we've come up with what we call the soil carbon index. And this really accounts for the differences between soils. As Kerry said, soils differ all over the place, they even differ within a field. And you have to take account of that because that affects how much you can store. So very simply, this will be covered in a minute, by the way, that's a mistake. Soil organic matter and clay are a really good indicator of this capacity to hold carbon in the soil. So it was a colleague, Tony Dexter, actually came up with this line here. This is a 1 in 10 line over organic carbon over clay. And Tony worked out from some soils in Europe that that's approximately where you get full coverage, if you like, of the clay on that line. If you're below there, it's undersaturated. If you're above there, it's oversaturated. So sort of the capacity measure. And then others went on with some other soils, actually European soils, and put in some other numbers, 1 over 13 and 1 over 18. And below 1 over 13, the structure we know is very degraded. And as you go up, it becomes better and better. So very good soils are over 1 and 8. So I'm just going to show you some evidence. We've tested this in the soils of England and Wales. We've got a national soil inventory, almost 4,000 soils. Here's the survey. It's on a regular grid across England and Wales, as you can see. And we've chosen the soils indicated there. So arable, ley grass, permanent grass, and woodland. And by the way, not peat, because of course peat is not controlled by clay. Peat is more organic. And actually, the residence of the organic matter there is controlled by things like, wetness and cold conditions is what controls the carbon. So we're basically looking at mineral soils here with different land uses. I'm going to quickly go through this because it illustrates how different management affects this ratio. So in the survey, if you look at woodlands, you can see that hardly any of them are in this area down here, which is called degraded. So it's a very good example of a natural system which has this high quality, if you like. You go to permanent grass, pretty similar actually. There are a lot of soils there above that yellow line in very good condition, and very few below that purple line, which is degraded. So that's the 6%, very small percentage. But then as we move into more stirring up of the soil, you can see with ley grass we go up to 15% degraded, and then the distribution of arable is about 38% degraded. Now actually for arable soils, I'm going to point to this area here. This is the 38% degraded. There are an awful lot of points in there because they're all on top of each other. And that's a long history, I think, of tillage basically, because that releases the carbon from the soil. And there are degraded soils that we can actually do something about if we want to improve them and to increase carbon storage. So the next question was, has the survey changed over time? We actually chose some of the sites which had not changed land use over 15 years. They were resampled. And actually this summarizes that all except the woodland here because this is the first one, this is the second one. After 15 years, all of them were becoming more degraded. So it shows the need for action, especially in the face of climate change, which has been mentioned a lot already. How do we improve the quality of our soils and the storage of carbon in our soils in the face of this continuing degradation, if you like, or lower storage of carbon, and the structure and also the biology and the function of the soils is less. So I'm now going to show just two benchmark sites because this is a different way of looking at things. I've shown national survey data, but you cannot, of course, know exactly what was done on the farm in terms of management, year by year, season by season. But we have two long-term experiments at Rothamsted and Woburn. So Woburn is a sandy soil with a low clay content. The Rothamsted is a silty clay loam, high in clay. And these are 70 years of data, of evidence. And it's actually the only picture I'm going to show with soil organic carbon only. Now that's interesting because nearly all the papers on carbon only talk about soil organic carbon on this axis. What does it show? These are layerable experiments. They're not the same treatments at the two different sites. But what does it show? Well, the low clay soil, the sandy soil, started off in arable. This is very low organic carbon, so it's 10 grams per kilogram. And basically, you don't need to bother about what the treatments are in detail. There's a bit of a fan shape. The ones towards the top have lays in them, they have grassland in them. The ones that are below the middle line, basically arable, so they haven't got any permanent cover, they've got a lot of tillage. Same sort of thing on the Rothamsted soil, but because this is only soil organic carbon, you can see that this started with pasture before this treatments were involved. The ones with lay or grass, particularly permanent grass, go up. The ones that are arable, they go down. And you can see the sort of time period over which they go down. It's quite a long period of time. If you look at that, though, on the index, which is this soil organic carbon over clay, you can see the two sites become more similar. And again, all the treatments that go up are the ones with the lay and the permanent vegetation, and the ones with arable, they basically go down over time into a degraded condition. So you can reach, on even the sandy soil on the left, a sort of moderate to good soil condition as long as you have more permanent vegetation, you have less tillage. The arable, though, nearly always goes down. In fact, it always goes down. So the degradation that we've seen nationally, we can say, okay, in the arable it's due to tillage. With the permanent grassland, you may have noticed that's also decreased. And actually, we don't know why that happened. So I'm coming now to the next issue, which is, what can we do to store more carbon and improve the quality of our soils? Well, I think, we need some targets. And I think I've shown enough evidence that it's unlikely that all soil types, because we can now allow for soil types, because basically having the soil organic carbon over clay accounts for soil texture or soil clay content. But it's unlikely that all land uses and soils can reach the same target index if we want to use this as a target. So what we're proposing is that I showed you a lot of arables are actually down here. We propose that you could get them and still have some tillage, or better still, minimum tillage. But you can get arable soils above 1 to 13. Lay arable, which of course has more permanent periods of vegetation, could be above 1 to 10 from our evidence. And permanent grassland and woodland can be in the very good location, which is above 1 to 8. And those also infer, what I've just said infers that you can store more and more carbon as let's say you have a sandy soil, you can go from here to here. That's how much carbon, extra carbon you could store. If you have a more clay-rich soil and you start from here, you could actually store a lot more carbon in clay-rich soils. So we've taken account of the differences between soils, which, as I say, you hardly ever see any presentation about carbon storage. Just talks about the carbon number and nothing else. So, yeah, we're coming now to the end. So basically, to put it in a nutshell, there's a lot of talk about regenerative agriculture, and there are all sorts of different methods that people have, and definitions even of regenerative agriculture. I don't espouse any particular way of doing things, but the principles are here. So regenerative agriculture minimises soil disturbance by avoiding mechanical tillage is one of the things which stirs up the soil and releases carbon. To maintain or vegetation cover and a protective cover on the surface, particularly against erosion, is particularly important, using cover crops or even going perennial, even going woodland. So you can see the potential increase with woodland is amazing. And then finally, the one that often gets forgotten, which is increasing crop yields, really. So improving crop nutrition, we know from some of our long-term experiments, even increasing the amount of nitrogen, it increases the productivity and actually increases carbon in soil over lower rates of nitrogen. So don't forget about nutrients or inputs from nitrogen fixation, inorganic or organic fertilizers, and other things. If you've got limitation on productivity, for example, due to pH, low pH, then lime is an important thing, increasing the productivity, increasing the returns to the soil, and therefore increasing soil organic carbon. So I think if we're going to store more carbon, we have to think about where to do it best, which soils are most degraded, which ones need lifting up. Can we change all of these things? Can we change our management to store more and more carbon? So in conclusion, what I've been saying basically is all here. The clay is a factor determining the differences between soils in the way that they can store carbon. There are decreases in soil health and particularly structural stability, which can be improved by increasing soil carbon. But not all land uses, as you've seen from the data, can reach the same targets based on our survey type approach and also from specific experiments at benchmark sites. And the thing I haven't really talked about is to assess the potential for your type of land, your type of soil, your potential management. You then have to go on, and if you're doing things, you have to be able to monitor and validate and report that change over time and have that change last as long as possible. You're going to continue to do those things until you reach nearer to the upper potential, if you like, that maximum or upper equilibrium for your particular soil in your location and with your management. And I think, Chairman, that was my last slide. I'd like to thank my collaborators who've been working on this particular topic with me, and I thank you for your attention.
Yeah. Thank you, Steve.